a lot of us in the industry have been doing Option C M&V for a lot of years. And we do this weather normalization and we do these fits. And how do you tell if it's a good fit or not? We use R squared value, or at least that's what we've been doing for the last, I don't know, several decades, which would mean our entire life in this industry. But you know what? R squared maybe isn't the best method. It's not, actually. The CVRMSE, which you probably know about, is much better. And in this webinar, I'll show you where the R squared value just falls apart. And it's actually fascinating. If you've been doing Option C M&V for a while, you are going to be fascinated with what you see here. It will change your mind, and as a professional, you will grow. I hope you like it. So the topics we're going over, it's not a lot here. You only see 3 lines, but actually is a lot. I'm going to try not to talk at 1,000,000 miles a second. It also means I might not make it through everything, but I'm just not in a whirlwind mood today, so we'll see how it goes. So that's what we're talking about. Let's get going. So here's the hook, and I think this was in the email that Tyler sent out. This was, when I saw this was in Agami Reddy's paper. When I saw this, it was like, what? How is that? It's like, here we have 2 sets of data. They have the same CVRMSE, which means the same scatter from the line, from the fit line, but the R squareds are way different. One of them's a great R squared and one's awful. Huh. That to me was absolutely shocking. Here's another one, another picture. Here we have the same CVRMSE. Oh, but wait, look, one of them, the scatter is a lot wider than the other. And the R squareds are a lot different. Oh boy, so this is really kind of, when I saw this, I was like, wow, I really want to look into this. And that's what I've been doing for the last couple of weeks is, looking into this, and the seminar is the result of it. Okay, so my source, here's the paper. If you want to, look it up. So it's, yeah, I'm not going to read it. And the second one was written by Bill Curran for BPA, Regression for M&V, Reference Guide. Bill Curran wrote a lot of good stuff. His stuff is, it's really, let's say, it's a lot more accessible than a lot of work by other PhDs. I think Bill's a PhD, I'm not sure, but the other PhDs, sometimes they write for PhDs, and it's hard to understand. But Bill's is pretty darn good stuff. Okay. So I actually don't remember what I was going to talk about on this slide here, but here is a regression. I guess this is the basis of what everything is, what we're talking about. And when you do a regression, you have an R squared value, you have a CVRMSE, and there are certain rules of thumb that are used in the ESCO industry. Well, what are they? Well, people have been saying, we need an R squared. Actually, I think it's the next slide. We need an R squared of 0.75 or above. In the CVRMSE, yeah, it should be about 25% or less. That's pretty much what people were saying, or mostly they were saying, especially we just need an R squared above 0.75. Yeah, here's what these standards are saying. I don't know if they're standards, but what these documents are saying. So that you don't have to read the top one. So the IPMVP, it's all different now. I'm all confused by Evo. I don't know what they're doing anymore. It used to be one big doc, and now it's like 5 books. But anyway, they used to say you want an R squared below or above 0.75, and now they're just saying it's an initial check. What's it say? They don't give a number like 0.75. And so not really saying much here, but they don't talk about CVRMSE either. So that's kind of interesting. They talk a lot about this fractional savings uncertainty, which I'll get into, and I've talked about before, but I think I'm going to be able to explain it a little more this time in a more, let's say, lay understanding. We're engineers, we're smart people, but we're not statisticians, and I really don't like the statistician type talk. And I think what I'm hoping I've done in this slideshow is actually to make this statistics stuff understandable. And this is ASHRAE 14. This is 2002. There's a later one that was written. It cost all this money to download, and it's going to be a pain in the butt. I just didn't do it. So this, I had the old one. So this is what I had, and that's basically that's where the 25% came from. They didn't talk about R squared, but they did talk about fractional savings uncertainty, and both of these are based on that Reddy paper that I mentioned before. Okay, so let's talk about R squared. What I've taught in the past and what people, seem to know. I mean, this is, I teach these metrics classes. I ask people, what's R squared? And they, often I hear these words. It's not that I, preach them. I hear them from the people at Go. R squared is the goodness of fit. Okay, well, yeah, that's what it is. Really what it is, and you don't need to read this, I suppose, but it represents the degree to which the independent variable, which would be kilowatt hours, varies with the dependent variable, which in this case is heating degree days. In fact, that's the bottom line there. So, so it's just to what degree do kilowatt hours or no therms vary with heating degree days? That's what the R squared is. And the CVRMSE, they say, is a measure of scatter. It's the same fit, and it represents all the other variation that wasn't captured by the R squared value. Now you would think, okay, so if I have an R squared that's 0.96, does that mean my CVRMSE is 4? It doesn't. I would think that that's what it should be, but that's just not the way it is. Statisticians, they don't think like we engineers. So, but it represents any variation in usage not determined by weather. Okay, that's something. That's a step something. Okay, so I think we can take this further. So this is what I've already said. I'm just kind of restating it. But let's look at these equations. So here's the R squared, the official name coefficient of determination. We call it R squared value. And oh, you know what? I don't know if this is my latest slideshow. So because I guess it is. Okay, so what's interesting here is the top part of this is how far the bill is from the fit line. Okay, so YI is the bill, the Y hat, they call that Y hat, the Y with that thing on top with the, that is what the fit line thinks the bill is, okay? So the difference there is how far the bill is from the fit line. And then at the bottom, what we're looking at is how far the bill is from the average bill. Okay, let's look at the CVRMSE. So the top is how far the bill is from the fit line, and the bottom is the average bill. R squared was how far the bill was from the average bill. The CVRMSE is the average bill, okay? That is the big difference, because the top of these two equations are the same, kind of. All right, so that is the crux of it. So look, this may be kind of interesting to you, but it hasn't really, I don't think, or at least if I was you, I wouldn't completely understand what I'm talking about yet. So we need to look at some pictures. So yeah, that's what I mentioned. Okay, so what I did was I went and I calculated all this stuff with a spreadsheet and calculated the CVRMSE and the R squared value. Okay, so why did I do it in Excel and not using metrics or Option C software? Because I had the fudge numbers to make this work, right? So it was a lot easier to do that in Excel because I can put in equations that would change what the therm values are going to be. It wasn't fudging numbers; it was just changing equations. So here is I have two trends. Now, one trend has a higher scatter or higher CVRMSE. That's the second one. That's the orange one. So that's on the right, you can see. And they have exactly the same fit line equation. See, you can see them. Same fit line equation. All right. They have, but one has more scatter than the other. And look, the R squared is higher. So I guess that's what I have here. Two sets of data, both same fit line. One has more scatter. Of course, the CVRMSE is higher because that's a measure of scatter. But the R squared is lower. Yeah, that's what I meant to say. It's lower. Okay, that's interesting. That's interesting to me, at least. Okay, so more scatter means a lower R squared value. So let's see if we can figure it out this way. So more scatter is a lower R squared value. So here it is. So the top is how far the bill is from the fit line. Well, that is my scatter right there up top. So that's my summary. There's not much here, right? More scatter means fit's not as good, of course. More scatter is a lower R squared value. That seems to make sense. When I say seems okay, it makes sense. The R squared works, yeah. The fit's not as good. The R squared's, lower. Okay. Okay, let's look at another one. This is a trend with, they got the same slope. Okay, I just increased the intercept. That's all I did. I just increased the intercept. In fact, that's what I have here. So it's two sets of data, same scatter, Absolute scatter. What I mean is that this, one of the bills is off by, 502. It's off by 502 on both lines. Okay, so the same absolute scatter, but one is a larger intercept, as you can see. And what we get, the R squared is the same. But the CVRMSE is lower. Oh my God. So this is getting confusing. So, wow. Okay, so the scatter was the same though, but the CVRMSE is lower. Oh boy. So let's see if we can figure this out on the equation. So this is why, okay, the average bill. We're looking at the average bill. And on that second one, let me go back, on that second one, the average bill was higher, right? And so now we're dividing by a higher number. Therefore, the CVRMSE is going to be lower. The N minus P, N's number of bills, P is number of independent variables plus 1. So higher average bill means a lower CVRMSE. That's because we're dividing by average bill. So scatter is the same, but since it's a lower percent of the total bill, the CVRMSE is less. So that seems to work to me. I buy that. The R squared was the same in both, so the R squared works, yes, and the CVRMSE works. When I say works, that means it meets my smell test. I think, yeah, that seems logical. Okay, let's look at another one. So this one, what I did was I have the same average bill. So I added all the bills together and they're the same average, okay? So that's the same mean value. I also have the same scatter. You'll see the CVRMSE is the same. And making this data, wasn't hard. It wasn't hard at all. I didn't say, okay, in this point, we'll try 0.05. No, that didn't work. 0.06, no, 0.062. Oh, that's worked. That's not how I did this, actually. It was pretty easy to come up with these data sets, just using equations. So anyway, so we had two sets of data, the same mean value, the same scatter, but one has a larger slope. And you've seen this picture before. So we have the same CVRMSE, okay, because it's the same scatter, but the R squared is higher. So why is that? Well, let's look at the equation. So let's see, okay, there we go. So larger slope means a higher R squared value. Why? Because it's how far bill is from the average bill. That's it. So that's that Y with that. It's supposed to be a line, a straight line over it, but it's kind of a U shape. But that is the average bill. So it's bill minus average bill. If you have a steep slope, then there's going to be a huge difference between the bill and the average bill on these edges, on the right edge and on the left edge. Then the difference will be huge. And that is what's causing this to be larger, which is affecting the R squared. So, wow, okay. All right, so let's summarize this one. So we have the two already in here. Here's the third one. Steeper slope means higher R squared value. Now that makes sense because a steep slope indicates the independent variable has more effect on the dependent variable. Yeah, that does absolutely make sense to me. Yes, it does. A shallower slope may be a good model, but it might have a poor R squared value. We're going to talk about that in a minute. It makes me question the value using R squared to determine whether a fit is acceptable. R squared doesn't work here. The CVRMSE works. So let's go back again and look at this picture. So I'm saying the R squared doesn't work. I have an R squared in the first case, that's with the flat, the blue line, the flat one, of 0.1222. If you're using metrics or option C to do your fit, and you get this R squared value, you're going to say, oh, this sucks. I can't use this. I'm going to have to bill match. Well, you know what? Maybe that was a bad choice after all. And we're going to get to that because the CVRMSE is just fine. There's not a lot of scatter here. Okay, that's kind of interesting. So let's look at one last one. Now this one's a little harder to explain. So this time what I did was I have, let me see, this tells what I did. I had two sets of data, of course. One is a larger intercept, obviously, and I increased the scatter to get the same CVRMSE on both. I don't know if you remember, but 2 examples ago, I had the same CVRMSE on both, or no, I had the same scatter, same absolute scatter on both, and I had different CVRMSEs, and remember, because it's divided by, I think, by average bill. So here, what I did was I increased the scatter so that my CVRMSE would be the same. So CVRMSE is the same. but the R squared is lower. So higher average bill, same CVRMSE, which will mean more absolute scatter and a lower R squared value. Because remember, more scatter meant lower R squared. We got that from the first one we did. Yeah, wow. So I think the thing I would take from this is the higher the average bill, the more scatter you can have, the more absolute scatter you can have from the line and have the same CVRMSE. And that actually makes sense. So that makes sense to me. It's because it's a percentage of the average bill, right? So if you had an average bill that's 1 and your scatter was, let's say, let's say your average bill was 100 and it would vary between, you know, bills of like 10 up to 200. That's a lot of scatter, and you're dividing by average bill. You know, that's a lot. You might end up with a CVRMSE of like 70% or 80%. But if your average bill was 1,000 and the scatter was only by that same amount, which was, you know, 90, then the CVRMSE might only be 10% because it's only 10% of the total bill. So this does make total sense to me. So more scatter means fit is not as good, but it seems to work. So they both work to me. Okay, so I'm going to take this. This is all going to be wrapped up and make sense to you. Okay, so you might be thinking, God, he's telling me all this stuff and I can't follow it. It's going to make sense, believe me. All right, so this is what Bill Curran said in his BPA thing. Oh, don't read it. So I translated it. So here it is. So he said the R squared value can be thought as a goodness of fit test, but a high R squared value is not enough to say it fits the data well, nor a low R squared indicates a poor model. Oh, geez. So all these people, including myself, have been saying, oh, R squared value, yeah, you want it above 0.75. Well, he's saying now, maybe not. And you just saw evidence of this because, well, if there's a really low slope, you're going to have a low R squared value. So, maybe R squared isn't what we should be tuning on. Now, he came up with, or this is what he said, a model of the low R squared is acceptable when okay, so I'm going to go over this. The scatter of the Y values around the regression line is low. I guess that means the CVRMSE is low, and yet large in relation to the total scatter of Y values from the mean of Y. So that's the relationship of, you know, how basically it's a measure of slope. Is there a slope or is there not a slope? Because the mean of what, I'll just leave it there. Oh, I wrote in other words down here. So yeah. In a flat graph with a low CVRMSE, if the scatter around the line is greater than the scatter from the average bill. That was my translation. Okay, and he's got this other part. And the total Y scatter is much smaller than the scatter of the X values from the mean. In other words, the heating or cooling degree days varies a lot more than kilowatt hours. All right, so this is what he said. This would be a way to say, yeah, I've got a low R squared, it's 0.2 something, but you know what? I think it's a good fit. So I went and tried that on one of these, on this one. So that would be the orange one, where I had a really great CVRMSE of 4. Yeah, that's great, but a terrible R squared. And so I thought I'd give it a shot. So it is a flat graph with a low CVRMSE. Yes. Boy, I don't know what's going on. Okay, so let's see what else I did. So I looked at the scatter from the fit, and I looked at the scatter from the mean. Is the scatter from the fit more than the scatter from the mean? It wasn't. So this tells me maybe it isn't good enough. See, I'm gonna talk to Bill and ask him about this because I don't know this, you know. And then what we did was we looked at the variation of heating degree days per day and variation from the mean, and I saw there's a lot of variation for heating degree days, but not from the mean, not at all. So it passed that one. That was number 3. But number 2, I didn't think I really passed. Yeah, too bad, because it sure looked like a good fit to me. So how I do this? This is what I did. I can give you the slideshow if you want to look at those steps. I'm not going to go over those steps. Okay, let's take a step back. Actually, this is worth reading, so maybe I'll read it to you. Life can be much broader once you discover one simple fact. And that is, everything around you call life was made up by people who were no smarter than you. That is true. That is true. You know, that goes back to the whole Tony Robbins thing I was talking about earlier, you know, that I'm not good enough. Guess what? They weren't either. And you can change it. You can influence it. I think it's very important. And once you learn it, you want to change life and make it better because it's kind of messed up in a lot of ways. Once you learn that, you'll never be the same again. That's really funny. Okay. Okay, yeah, that was Steve Jobs. Okay, so let's get back to this. Fractional savings uncertainty. So I guess the question, we'll talk about why we're talking about this. So ASHRAE 14 in 2002 came up with this. Actually, Reddy came up with it in 2000, the year 2000. And this term on the left, that means fractional savings uncertainty. What it is the uncertainty. So that's the top part, the delta E savings. That's the uncertainty. And then E is the savings amount, how much is saved. So what's the percent uncertainty over the percent that's saved? That's why they call it fractional. Okay. There's a couple things that are important, or maybe one that's most important, and that is that one. It's the way it's calculated, it's divided by F, which is the amount of savings. If you think you're going to save 5%, then your fractional and savings certainty number is going to be big. If you're going to save 50%, then your fractional and savings and certainty number is going to be really small. And some other people came up with better ways of calculating this. It gets a little more complicated. I used the easy one. Oh, actually, I did the middle one when I was doing this. You'll see, because I've done a little bit of calculations on this. But yeah, they seem to get it better and better and better. What Reddy did in 2000, which was kind of cool, was he said, okay, let's assume a 68% confidence level. Oh boy, so I'm 68% confident that after 1 year, that is 12 bills, the savings will be, let's do this. Let me back up. So let's say we were looking at the very top one. If I had I assumed top left, I assumed I was going to save 5% of the utility bill. My CVRMSE was 0.05. Then I am 68% confident that my savings estimate is going to be off by about 39%. Okay. All right. Now, people, you know, so let's not go into that part yet. The fact that I don't want to say this to my clients. We'll get to that in a minute. But I think that's what's worthy of looking at first is the fact that you can make a table like this. First thing is, as the fraction, the amount of savings, that's F, the amount of expected savings increases, the fractional savings uncertainty, that's FSU, Fresno State University, that will go down. Okay, that makes sense. And as the CVRMSE increases, then yes, the fractional savings uncertainty should also increase, right? You want the smaller CVRMSE. Okay, I buy that. But what's really cool is you can make that table. The problem is people maybe don't want to say, I'm only 68% confident in this number. I don't know if 68 is a number people are going to want to use. Maybe they're going to want to use 90 or 95. I don't know. So he also did one with daily data. And the reason I showed you that is, this is something actually I'm not too happy about, but if you compare these two, I think, oh boy, I think I lost something here. Smaller intervals are going to decrease the fractional savings uncertainty. So let's look at the top right, a CVRMSE of 5% more or less, and you plan to save 40%, you're going to be off by 4.9%, at least for 68% confident you'll be off by 4.9%, as opposed to less than 1%. So having more points, they're saying is really important for decreasing this fractional savings uncertainty. Look, I'm just an engineer. I'm not a statistician. I don't buy it, but they do, and they know a lot more than I do, but it just doesn't smell right to me. But I know, I don't know. This is something I want to fight, and I started arguing with Bill Coran about this, but to no effect so far. Okay, so the level of uncertainty at a confidence level of 68%, the level of uncertainty should be less than 50%. So I went and calculated all this stuff, and here is the result of what I calculated. And this is actually kind of interesting. So these are all the different cases that I showed you graphs for. and then this is what these are my assumptions down here. So monthly data, 12 bills before, 12 after, one independent variable, 30% savings expectation. So that F was 30%. I thought that might be good for a typical performance contract. All right, now what's interesting here is I divided fractional savings uncertainty by CVRMSE, and look at that, it's a constant number. That's pretty darn cool. So now that only is true though for a certain, I didn't mention that. I guess that got lost, but it is based on a certain confidence factor. So I think I used 90%, and that's, so if you had 68% or 70%, 80%, then this ratio is going to be different. But what this means is that it means that you could actually make your own tables, just like Reddy did. That's kind of cool. So it's not that hard to calculate this. You could do it, but it's hard. Other things are hard. Also, it's not related to R squared at all. It's proportional to CVRMSE. Fascinating. So like I said, you can make tables. There's 3 inputs, CVRMSE, F, and F means the fractional savings, how much you expect to save, and the confidence level. Okay. What now? So what if you have a good CVRMSE and a higher CV, or a good R squared, higher CVRMSE? Oh, like this one right here. So I circled one. Okay. So yeah, it's good. So that's a good fit, right? R squared is 777. That's good. CVRMSE, it's a little high, but it's okay. I have a fractional savings uncertainty of 54.5. Not so good, according to ASHRAE 14, 2002. But that is at 90% confidence. And you know what? They said just look at 68%. At 68%, it would have been 31.5, which they would say is fine. So I guess it is okay. Okay. Now, I've thrown a lot at you, so let's start getting to summarizing everything I've said. What if you have a good, okay, this is the same stuff, same exact thing. This is my thinking, and I could be wrong. If I was an ESCO, an M&V guy, I don't think I would want to go and tell him, look, I'm 90% confident that the savings are going to be off by 54.5% or less. I just don't think they're going to buy that. It's like, wait. Did I make the savings or did I not? Well, I don't really know. I'm 90% confident that they're going to be off by less than 54%. And if you ask me, a client, or at least if I was the client of a performance contractor, I would say, oh, you mean you're saying that you're going to fudge the results by 54.5%, or maybe you'll give me the 0.5%. You're going to fudge them by 54%, right? And increase it, so therefore, then you don't have to write me checks. Is that what you're saying? Because that's what, especially a skeptical client's going to say. I just don't. To me, that's where statistics just doesn't meet, people. What Reddy was saying is, in that paper, that you might want to submeter these buildings where you have a bad, damn it, I'm sorry, the fractional savings uncertainty is too high. You might want to submeter those buildings instead. But you know what? We're going to put off building the retrofit for 12 months. How much money is going to be lost doing that? So I don't think that's going to work. So here's what I think, and this is just me. And you guys might come up with your own conclusion, which is better, and I'm good with that. My job isn't to tell you what to think. My job is to tell you what I know or what I've learned. So I think the best solution is, look, just tune your metrics and Option C projects to the lowest CVRMSE, and usually the lowest CVRMSE is usually at the best R square values anyway. And just decide the fit's acceptable based on this CVRMSE is less than 25%. Forget the R squared. Use that. That's my advice. But you will do what you think is right. So you might have an R squared of 0.6, but the CVRMSE is 20. I would now advise take it. Okay, so let's talk about, I don't think I made a slide about this, and so let's do this now. So let's say you were tuning all along for 75% R squared. That's what you were doing. Were you doing things wrong? No, you weren't. Basically what you were doing is you were doing probably a more conservative method of tuning. If anything, it means that you had some flat fits that you chose to bill match rather than use weather normalization on. That's all it means. It means you dropped weather normalization on some fits where weather actually didn't have a lot of play anyway because it was a flat line. So, you know what? I don't think we've really strayed too far. So basically, let me repeat what I just said. So have we erred by going with R squared is, greater than 75? My answer is no. What if you picked any fit with an R squared over 0.75, the odds are the CVRMSE was just fine. I'd say that's probably true for 98%, 99% of the cases. There's one case in class where that's not true, but that's generally not true. Okay, so we haven't made mistakes there. But the one place where you might have done things differently is when you had an R squared that was low, in the past you might have bill matched it. And now instead, I'm saying maybe you could let it go and actually take a low R squared tuning, as long as this CVRMSE is low, okay? So that's it. And then, so then you might say, well, yeah, that means that I lost all the weather normalization, that I could have done. Yes, that is true. But these low R squared meters were probably meters that were very flat. They had a flat slope, which means there was not a lot of weather variation, which means that there really isn't a lot here. There's nothing really here to see. So let's see. So here's my summary. R squared is not as useful as you think. It's affected by slope, intercept, and scatter. You can calculate a fractional savings uncertainty. I don't know if it's going to be useful to you. CVRMSE maybe. I use the word maybe. I learned that in engineering school. You say that instead of saying is. It may be a better indicator because it does not vary with slope. And that's it. Hey, Tyler, can you take over?
Yeah, absolutely. Looks like we have a couple questions already in the chat box there, John.
Okay, let's see what we got. Okay, he said, do you recommend eliminating outliers to get the data more in line? Yeah, it depends, you really need a story. If you know, it's really weird. ASHRAE 14 is kind of funny about that. I don't know if the IPMVP says much about that, but the ASHRAE 14 has like these two different ways of doing M&V with option C. And one way they say you got to calculate fractional savings uncertainty, which I've never seen anyone do. And if you do that, then I think then you can deselect bills. But if you don't calculate fractional savings uncertainty, then you're not supposed to deselect any bills ever. But I don't think anyone's really following that. And this is based on the 2002 version, and I'm sure it's changed since then. I'm sorry, I don't have the latest. But basically when it comes to deselecting outliers, if it's an obvious outlier, I think you should deselect it. That's just me. I'm just a software guy. Yes, I guess I have an engineering degree, but I would deselect it. Yes, certainly. It's best if you could document why. So, you have a bill, it's like the March 2017 bill. Go back to the facility operator and ask, what's going on? What happened in March 2017? See if you can get some information and then document it. Just because you never know when someone's going to be looking over your shoulder, and you never know what their prejudices are, or if they think that, ESCOs are they might love ESCOs or they might hate ESCOs. And if they hate ESCOs, then they're going to look for ways to nail you, and that would be one. Okay, so that's that. I got one question, that's it. Anyone else got any questions?
That usually means you did a good job.
No, it could also mean I bored the crap out of everyone. You guys, I don't know if you think this one was interesting, but I totally enjoyed this one. I really researched a lot of it on this one, and it was pretty darn neat stuff. So that's what we got. Thank you, guys. I can't believe you're still here listening to me. Yeah, that's it. I'll see you in a month. I'll see you, or I guess in a couple weeks.
Enjoy the rest of your week, guys.
Bye, everyone.